Cryptographic algorithms are based on hard mathematical problems, and the security depends on the hardness of those mathematical problems so that you can execute a function to encrypt or sign something, and actually reversing that without the correct keys becomes very hard. Recovering the keys is mathematically intractable. And although there are algorithms which in theory could recover the keys and break the cryptography, they would take too long to run on the most powerful supercomputer we have available today.
I mean, what are we talking about?
Millions or billions of years.
Goodness. Well, I can say confidently that they are safe from me breaking the security because I am not great at math and I certainly would not be able to keep up with what a supercomputer can achieve. And it's good to put a number actually on quite how secure the algorithms currently are. We say they're pretty much unbreakable, but billions of years on the most powerful supercomputer in the world? Like, wow.
It's quite something, isn't it? And as you might have guessed, that was our guest, Nigel Edwards. And we are returning to the topic of post-quantum cryptography, or PQC, to get an update on how things have changed in the past year. I'm Michael Bird.
I'm Sam Jarrell.
And welcome to Technology Now from HPE.
So why exactly are we returning to a topic we have covered before on the show, Michael? Could it have something to do with the near weekly articles about a new, quote, breakthrough in quantum computing?
It does seem like the progress is accelerating. And with the knock-on impact of a quantum computer on our security infrastructure, it is pretty important to keep up to date with the latest security landscape.
This security landscape would, I assume, be having to respond to any developments in the quantum computing world. I mean, if there's effectively an inbuilt deadline by which any sort of quantum secure algorithms would have to be ready to be deployed by.
Yeah, and as you'll hear in my chat with Nigel, that deadline is closer and approaching faster than originally expected. But it's not just software which is threatened. Some hardware can have security physically baked into the silicon. And in cases like that, a simple update to the security might not really be enough.
Because you would need to fully replace the hardware?
Among other things, yes. So this week we're hearing from Nigel Edwards, who is director of the security lab at HPE Labs. We chatted a little under a year ago about PQC. So the first thing I wanted to know is what's changed since we last spoke?
So a couple of things I think caught my eye over the last 12 months or so. So my colleagues who are researching quantum computing, together with their colleagues in the Quantum Scaling Alliance, published a white paper on how to build a quantum supercomputer. So they're working with companies, some of the top academic institutions as well, outlining how you would go about producing a quantum computer built of quantum processing units. And then secondly, just recently, a significant white paper was published by a couple of the US government research labs, the National Energy Research and Scientific Computing Center, or NERSC, and the Lawrence Berkeley National Lab, published a survey of the academic literature on quantum computing. And what they've seen is that there's a constant trend of the amount of resources required to apply to quantum algorithms being reduced. And also they looked at what the claims are being made by the vendors of quantum computing devices. Some of them are claiming that over the next 10 years, there will be a 1 billion factor of improvement. If anything, there's an acceleration of progress that's occurred over the last 12 months.
Because last time I think we talked about there being a timeline for when organizations should start to think about it, but that was something like 2030, 2035. But are you saying that timeline that organizations need to be prepared?
The three key dates that we had 12 months ago, looking at the recommendations from various government agencies around the world, was have your plans in place by 2028. And then for your high priority systems, complete the migration by January the 1st, 2031. And then all migrations by January the 1st, 2035. 2035 is now looking maybe a little bit too late, in my view. And I would, for all systems, be looking to get it done in the early 30s.
And do you think organizations will have it all done?
I think there will be challenges. And I think organizations need to prioritize. I think the advice on that is not to change the strategy. You need to inventory your systems, inventory your services, and then focus on the ones that are top priority, on which your business depends. Systems that are manipulating or managing sensitive data, such as personal information, financial systems, telecommunication systems, systems with medical records on, all of those are high priority.
So what physical qualities are needed to make a quantum computer cryptographically relevant? Like, why aren't we worried today?
So today, there just isn't enough power in the quantum computing devices. And the engineering challenges are to create a sufficient number of logical qubits. So perhaps the most famous quantum vulnerable algorithm is RSA. So to factor a 2K RSA key, you need roughly 2,000 logical qubits.
Hi, VoiceOver Michael here, just a quick one. For those who haven't come across the concept of a logical qubit before, it's basically a type of quantum error correction. A physical qubit is the actual thing which is in the quantum computer, whereas a logical qubit is created using multiple physical qubits, which all work together to simulate a perfect qubit without errors. It's more resilient to noise than the physical qubits. Anyway, back to Nigel.
Now, a logical qubit is not the same as a physical qubit. And the challenge is quantum noise. The more physical qubits you put together, the more noise you generate. And then you have to use quantum error corrections. And then using quantum error correction to correct that noise becomes more and more challenging.
So there will be a cliff edge. Like once that golden number is achieved, then particular RSA keys can be
cracked. Some of the technology vendors working on quantum computing devices are saying exponential growth, right? So it's the equivalent of Moore's law, but in the quantum computing space. And some folks are predicting an increase of 1 billion over the next 10 years, a number of logical quantum bits that are available. So at that rate of progress, is pretty much as soon as a 2K key is successfully factored, then 3K and 4K keys are going to fall very, very quickly after that, which basically means that RSA is no longer viable.
So how is the industry responding to these changes of the impending cryptographically relevant quantum computer?
We are working on deploying post-quantum cryptographic algorithms. So these algorithms were standardized by NIST earlier this decade. The standards were published in 2024. We are working on applying these in our software stacks, our firmware stacks, and making changes to silicon. The long pole in the tent are the changes required to silicon, because you cannot instantly change silicon to handle new cryptography. Chip designs and changes to chips, a typical life cycle is 2 years, in some cases as many as 4 years. So if a standard is published, then it's not reasonable to expect that to appear next year or even possibly the year after in silicon.
So what's the impact then? We have to redesign every single component or every single chip?
It's not a complete redesign, but we need to make certain changes to the chips. So in particular, when you look at how firmware is required for the processor, for example, an x86 processor to execute x86 instructions. So that firmware is verified by keys that are fused into silicon to ensure, for example, it's genuine firmware. These keys are your classical keys, such as RSA or ECDSA keys. They need to be changed to use these post-quantum cryptographic algorithms, which have been standardized by the National Institute of Standards and Technology organization.
And so does every single component have to be updated at the same time, or can you sort of piecemeal it as you go along?
So the approach that we are taking in HPE is to be able to offer our customers PQC configurations with our newer products, PQC-enabled configurations. We know that not all components that are available will be PQC enabled, but we are working with our supplier partners so that there will be a network controller, a storage controller that we can source that will be PQC enabled together with PQC enabled processors, so that the components that matter inside that server, for example, will be PQC enabled.
I think you talked both about PQC enabled and PQC capable hardware. What is the difference?
So we tend to think of it at a product level rather than specific hardware. PQC enabled means all the cryptography in that server is running the PQC algorithms. PQC capable means it's capable of running those algorithms, but it might not be enabled. But it could be enabled in the future by configuration changes and possibly software and firmware upgrades.
So how should an organization then be preparing for this transition? Like, should they be buying the correct hardware today, or is it more of a planning phase at the moment?
So today, the hardware is not available. There is not a PQC-enabled processor available. And so right now, my advice would be to start planning. You need to know the critical systems, because this is not going to be just a turn of a switch, right? You need to understand how you're going to upgrade your systems, when the upgrade is planned. You need to look at how you're going to refresh the hardware, look at how you're going to refresh the software stacks as well.
This conversation has been quite hardware focused, but presumably that has a knock-on impact to the software that you're running.
Right. The operating systems will have to change. The services running on the operating systems will have to change. Some changes are being made to software. A well-known web browser, for example, already has some PQC algorithms running in it. Software is a little different to hardware because software can be upgraded in the field. Hardware is much harder to upgrade in the field and much more expensive. It's not a question of patching. You've got to open up the chassis and pull out the components. And to upgrade a current generation server to a PQC-enabled server, that would require changing the motherboard.
We've talked a little bit about some of the practical points, but just dive a little bit into PQC, maybe a bit of a PQC 101. Like, why is it resistant to a quantum computer? And maybe how does that compare to why RSA is vulnerable to a quantum computer or other encryption methods like RSA?
Cryptographic algorithms are based on hard mathematical problems, and the security depends on the hardness of those mathematical problems, so that you can execute a function to encrypt or sign something, and actually reversing that without the correct keys becomes very hard. Recovering the keys is mathematically intractable. And although there are algorithms which in theory could recover the keys and break the cryptography, they would take too long to run on the most powerful supercomputer we have available today.
I mean, what are we talking about?
Millions or billions of years.
Yeah, that's too long.
And the problem is that quantum computers are a completely different model of computation to current hardware. And that allows them to run algorithms in a reasonable amount of time on a quantum computer, where it's not possible realistically to run it on a classical computer. And so what that means is we have to find new algorithms which are based on problems for which there are no known quantum algorithms. And so this is what the cryptographic academic community have been doing, and what NIST have been evaluating proposals from the community over more than a decade to determine the algorithms which are best suited to protect us from the threat of a quantum computer. So the algorithms they standardize, there is no known algorithm which will run on a quantum computer that will compromise the security.
But I suppose compared to encryption methods like RSA that have been around for decades and are very widespread in their use, a PQC algorithm is maybe less stress tested. How do you make sure that actually those algorithms or those encryption methods are actually good encryption methods?
So there is a school of thought that the new algorithms, some of which were only standardized in 24, they're not battle hardened, they're not sufficiently field tested, whereas we understand RSA very well, for example, which has served us for multiple decades, and we know the properties of that. And there are some eminent people, and there's even some EU government institutions that are saying that you cannot discount the possibility of there being either a flaw in the algorithms, and almost certainly will be flaws in implementations of the algorithms. So the strategy that we're adopting in HPE is to sign software and firmware with both a classical RSA or ECDSA key, as well as with one of the newer quantum algorithms. And what that does is it extends until somebody has a cryptographically relevant quantum computer. If there were to be a flaw in one of the new PQC algorithms, then provided there is no cryptographically relevant quantum computer, we still have security. Meanwhile, analysis on the new algorithms and the implementation of those new algorithms will continue. we're not throwing away the classical algorithms. We are using those as well as the new algorithms to provide the best possible security.
Nigel, thank you so much for your time. It's been an absolute pleasure interviewing.
No, it's been a pleasure. Thank you.
Wow. The fact that we've already moved the safe migration date of 2035 closer to 2031, and it's been a year since you last talked to him, that's a massive acceleration. That makes me wonder if in a year from now, he'll be like, oh yeah, actually it's next year.
Yeah, they are predicting a 1 billion factor improvement over 10 years. I mean, it was serious a year ago and it's serious now. The fundamental factor here is that once there is a cryptographically relevant quantum computer, our traditional methods of encryption no longer work.
I highly doubt most organizations have really grasped that for many of them, it is too late. And they'll be playing a lot of catch up to get their hands on what they need to upgrade their systems. And this is going to change the game because once the tech is out there, nefarious folks are going to start figuring out how it ticks for themselves. This is a massive cybersecurity gap for everybody.
It sort of feels a bit like the Millennium Bug, Y2K.
Yeah.
But we don't actually know when the date is.
It's a little bit scary to me. But like he said, there are things you can be doing right now. You can be planning right now on what you will need to do. And I found it quite interesting that he even mentioned that there's already a well-known web browser that's running quantum algorithms. So people are doing some things, right?
Yeah. And so I think that's the thing. Once there is a cryptographically relevant quantum computer, processes would need changing. If you think things like banking apps presumably would need updating, any sort of applications that use cryptography, there's going to be a serious amount of work which will be required. Of course, we've been using RSA or classical algorithms for years, whereas the post-quantum cryptography algorithms, they are really in their infancy, maybe 5-10 years old to some extent. They haven't really been stress tested because they aren't the algorithms in use. They haven't had as much widespread use. So this concept of locking a door with 2 padlocks seems like a very sensible thing to do.
I'll be interested to see once they are able to start stress testing these things. Can you imagine being the folks who have the job of trying to break them? I imagine people will be working on breaking them right away, both governments, institutions, bad actors, all kinds of different folks. We've mentioned how quick this deadline is coming up, but do you think the average consumer has any idea this change is coming? What would you tell them? It basically update your browsers and don't worry?
I'm so glad you asked, because the last thing I wanted to ask Nigel was this. As consumers, how should we be responding to the threat posed by a cryptographically relevant quantum computer? To your point, do we need to change our browser? Do we need to change our phones? So I thought Nigel's answer was really interesting.
You need to keep your software up to date. There are some web browsers out there that are deploying these new algorithms, and they're protecting against the so-called harvest now, decrypt later attack. So already some web browsers are protecting that, so you need to keep your software up to date. And then over time, as you buy new phones, buy new computers, the reputable vendors will be ensuring that those have the new PQC algorithms inside them. I think if we do our job properly in the industry and well, you won't know that that is actually taking place.
Okay, that brings us to the end of Technology Now for this week. Thank you to our guest, Nigel Edwards, and of course to our listeners, thank you so much for joining us.
Yes, and if you've enjoyed this episode, please do let us know. Rate and review us wherever you listen to episodes. And if you want to get in contact with us, send us an email to technologynow@hpe.com. And don't forget to subscribe so you can listen first every week. Technology Now is hosted by Sam Jarrell and myself, Michael Bird, and this episode was produced by Harry Lampert and Izzy Clark, with production support from Alicia Kempson-Taylor, Becky Bird, Elissa Mitri, and Janessa Ayosh. Our theme music was composed by Greg Hooper.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green. And our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a Fresh Air production for Hewlett Packard Enterprise, and we'll see you at the same time, the same place next week. Cheers.
Bye, y'all.